Okay, this is a review for exam 3. Let's get this ready. Okay, so for question 1, to show that two given functions are inverses, you've got to show two things. You've got to show that f of g of x is equal to x, and you also have to show that g of f of x is equal to x. You have to show both of those things. So starting with f of g of x, that means the g function is going to go inside the f function. So here's the f function, and anytime there's an input or an x, I'm going to leave an empty parenthesis. So cube root, and then instead of x plus 3, I'm going to put parenthesis plus 3, and then minus 2. And then in that empty parenthesis where x used to be, you write that g function. So negative 3 plus x plus 2 to the third power. And then what's supposed to happen is everything cancels except for that single x. So first thing that cancels is that negative and positive 3. So now we have the cube root of x plus 2 to the third power minus 2. Now the cube root and the third power cancel. So we have x plus 2 minus 2, positive negative 2 cancel. So we show that f of g of x is equal to x. So that's part of it. The other part now is to show that g of f of x is equal to x. So now the f function is going to go inside of g. So I'm going to rewrite the g function here. So g of f of x can be negative 3 plus, then instead of the g function, as you can see here, is x plus 2 to the third power. Rather than x, I'm going to leave empty parenthesis plus 2 cubed. And this empty parenthesis here gets filled in with the f function, which is cube root of x plus 3 minus 2. Okay, and now again, hopefully everything cancels except for an x. So the positive and negative 2 can cancel. Then cube root and the third power cancel. Then positive and negative 3 cancel. And you're left with x. So that proves that f of x and g of x are inverses of each other. Okay, first task is to find the inverse. So remember, in order to find an inverse, we switch the place of x and y, and instead of f of x, you can think of that as y. So the first step would be to switch that y to an x, so x equals square root of y minus 1 plus 4. And then I'm going to subtract the 4. Then I'm going to square both sides. And then I'm going to add the 1 to both sides. So the inverse is x minus 4 squared plus 1. Now, that is a quadratic whose graph typically is a parabola. Now, the only difference here is this is not a typical quadratic or a typical parabola. It's an inverse. And let me try to explain what that means. the next step here is to graph the original function and the inverse function. So the original function is a square root. Typically square roots start at 0, 0 and just kind of come up and to the right. This one's moved to the right 1 and up 4. So right 1, up 4. So there's the starting point. Let me just keep track of a couple of points here. So we have a point of 1, 4. Now, if I plug in a 2 for x, 2 minus 1 is 1, square root of 1 is 1, 1 plus 4 is 5. So the point 2, 5. If I plug in a 5 for x, then 5 minus 1 is 4, the square root of 4 is 2, and 2 plus 4 is 6, so 5, 6. So, it's the graph there. We can see from that graph that the domain is from 1 to infinity. We can also see from the graph that the range of f of x is from 4 to infinity. Now, to find the graph of the inverse, we switch the place of x and y of the original function. So if this is f of x, then the inverse is going to have this same table, but the x's and y's are going to be flipped. So I'm going to have 4, 5, 6, and then 1, 2, 5. So 4, 1, and then 5, 2, and then 6, 5. So this is the graph of the inverse. Now, that's what I was trying to explain earlier. The inverse, x minus 4 squared plus 1, that's a parabola, but because it's an inverse, it's only the right half of the parabola. If I were to graph the whole parabola, it would look like this. But we're not graphing the whole parabola, we're only graphing the part that's the inverse of the original function. So, this is the graph of f. Oops, let's get the pencil back. This is the graph of f. This is the graph of the inverse. And then the domain of the inverse would have been the range here. So the domain is from 4 to infinity. And then the range of the inverse is the same as the domain of the original function, which is 1 to infinity. So I think we got everything answered there that needed to be answered. Okay. For 3 and 4, we just need to find the inverse. Remember the way to find the inverse is switch the place of x and y. So considering g of x to be a y, the first step would be switch the place. And then subtract 1 on both sides. And then raise both sides to the third power, because the cube root and the third power are opposite operations or inverse operations. And last step is to add 2. So we have x minus 1 cubed plus 2, and this is the inverse of g. For question 4, same idea, a little trickier to finish, but it starts the same. First step is to switch the place of x and y. The reason this one's a little trickier is there's 2 different y's that we need to try to get down to a single y. So the way we do this is split up the fraction, first by multiplying both sides by the denominator. So now we have, and then I'm going to go ahead and also distribute that x. So I'm going to get yx minus x equals y plus 4. Now I want to get this y to that side, so I'm going to subtract it. And then I want to get this x to that side, so I'm going to add it. So now I've got y, x, subtract y equals x plus 4. And the reason for getting all those y's on the same side is now it's a common factor. I can factor out a y, and that leaves x minus 1. And then I can divide by x minus 1. And this is the inverse. Now the remainder of this video was actually a combination of a video I made a few years ago that I had to combine with this video file, so the numbering might be a bit off. This ended on question 4, so the video I'm going to mash up with this one starts again on question 1. It would be question 5 of the review that's been posted for Math 1055. So just be aware that the numbering is a bit off, but they're the exact same questions. So.
Okay, first 4 questions are graphing. There's similar methods of graphing both exponential and logarithm. Question 1 is an exponential function. The way this was presented, really 3 steps, I guess. The first step is to locate the horizontal asymptote. That's found from the vertical translation here at -1. That means the horizontal asymptote moves down 1 unit. Step 2 is to locate the y intercept. That's found by letting x equal 0. So we put a 0 in for x. 0 minus 1 is -1. 3 to the -1 is 1/3. 1/3 minus 1 is -2/3. That's about right there. Third step is to find 2 other points on the graph. So if x equals 1, for example, 1 minus 1 is 0. 3 to the 0 power is 1. 1 minus 1 is 0. So 1, 0 is on the graph. If x equals 2, 2 minus 1 is 1. 3 to the first power is 3. 3 minus 1 is 2. So there's the graph. Now it doesn't specifically ask for it on this question here, but it may on the exam, the domain and range. The domain is all real numbers. The range doesn't include -1, but it's from -1 to infinity. Okay, question 2. Same 3 steps. Locate the horizontal asymptote, locate the y-intercept, and then find a couple other points. Same thing, we have a vertical translation here, down 1 unit, so the horizontal asymptote is located at -1. Y-intercept is found by letting x equal 0. Place a 0 in there for x. 0 minus 2 is -2. 1/3 to the -2, let me write that up here. 1/3 to the -2 is the same as 3 squared, so that's 9. 9 minus 1 is 8. So 0, 8. Now, for that x equal 1, 1 minus 2 is -1. 1/3 to the -1 is the same as 3 to the first power, so that's 3. 3 minus 1 is 2. 1, 2. Then if we have a 2 for x, 2 minus 2 is 0. 1/3 to the 0 is 1. 1 minus 1 is 0. Even though these are both considered exponential functions, question 1 is an exponential growth function, question 2 is an exponential decay function. Here the domain is all real numbers. The range is -1 to infinity. Okay, the steps are similar for graphing logarithmic functions, but instead of locating a horizontal asymptote, we're locating a vertical asymptote. The vertical asymptote is found by following the horizontal translation. X plus 1 is a horizontal shift to the left, 1 unit. Then we locate the x-intercept. That's found by letting y equal 0. Now f of x is really the same thing as y. So if we put a 0 in for y, we have to solve for x to find out what the x value is. We're going to add 1 to both sides. That gives us the equation 1 equals log base 3 of x plus 1. If you exponentiate both sides with a base of 3, that takes care of the logarithm over there. 3 to the first power is 3, so we have 3 is equal to x plus 1. That means that x is equal to 2. So the x-intercept is 2. Now we're going to do the same thing that we did up here. We're going to find a couple of other points. It might be easier with logarithms, instead of choosing the x values like you normally would, to choose the y values. For example, if you choose a y value of 1, I'm going to say 1 right here. If you add 1 to the other side, you're going to get 2 is equal to the log base 3 of x plus 1. Exponentiate both sides, you get 9 is equal to x plus 1. So x is equal to 8. We could let y equal negative 1 here. We can see what happens. So if we add 1 to the other side, we get the equation 0 equals log base 3 of x plus 1. Exponentiate both sides. We get 1 is equal to x plus 1. That means that x has to be 0. So there are a couple of points we can plot. 8, 1, 0, negative 1. Here the domain is from negative 1 to infinity, and the range is all real numbers. It doesn't include negative 1 because that's where our vertical asymptote is for the domain. Okay, question 4. Vertical asymptote is located by following the horizontal translation. X minus 2 is a movement to the right 2 units. Now we need to find the x-intercept by letting y equal 0. So we place a 0 right in here. If you add 2 to the other side, you get the equation 2 equals log base 2 of x minus 2. Exponentiate with a base of 2 on both sides. 2 squared is 4, so we have 4 equals x minus 2. X equals 6. So there's the x-intercept. We want x to equal negative, or y equal negative 1 here. So we put a negative 1 in place of y. Add 2 to the side and get the equation 1 equals log base 2 of x minus 2. Exponentiate with a base of 2. 2 to the first power is 2. 2 equals x minus 2. That means that x equals 4. So we have 0.4 comma negative 1. If we let y equal negative 2, and the reason I'm choosing smaller y values, if I let y equal 1, it would be a point way over here on the x-axis. So you can graph it if you want, but I'm choosing some smaller values of y to get smaller values of x. So if this is negative 2 for y, and you add 2 to the other side and you get 0 equals log base 2 x minus 2. Exponentiate with a base of 2. 2 to the 0 power is 1. 1 equals x minus 2. So we get an x value of 3. So the domain here is from 2 to infinity, not including 2. The range is all real numbers. Okay, this next section is pretty easy, just rewriting. If it's in logarithmic form, you can exponentiate using the same base. So you have 216 equals 6 to the third. Here you use a base of 9. So that's gone, and you have 81 is equal to 9 squared. Here you can use a base of 13. So that's gone. You have 1 is equal to 13 to the 0 power. Here you use a base of e. You have 155 equals e to the x. The next section is just doing the reverse. They're already in exponential form. So you have to rewrite using logarithmic form. To cancel that base of the 2, you have to use a log base 2 on both sides. That's gone, so you have 6 is equal to the log base 2 of 64. Here you use a natural log. So you have x is equal to the natural log of 216. Here you use a log base 289. So you have 1/2 equals log base 289 of 17. Here we're going to use a log base 8. 2/3 equals a log base 8 of 4. So now this next section is evaluating logarithms using properties of logarithms. One of the properties that we talked about is regardless of the base of the logarithm of 1 is always equal to 0. Log base 16 of 4. The trick here is to try to get try to change the 4 into 16 to some power. So log base 16, 4 is the same as 16 to the 1/2 power, because a power of 1/2 is just a square root. The square root of 16 is 4. Now that we have matching bases, the answer is 1/2. We're in 15. We have to change 125 into 5 to some power. 125 is 5 to the 3rd power. Those bases cancel, so the answer is 3. Here, similar trick as in question 14. We're not going to change the base of the logarithm. We're going to change the 5 into 25 to the 1/2. 25 to the 1/2 is just the square root of 5. The square root of 25, which is now that they have matching bases, you get an answer of 1/2. A base of 3 and a log base 3 are inverses. Those just cancel each other out, so the answer is 8. Same thing, natural log is just a log with a base of b. Those have the same base, so the answer is 5. Next section here, use the definition of logarithmic function to find x. Essentially all they're doing here, all I'm asking you to do is to solve the equation. If we exponentiate using a base of 12, then we have x equals 12 squared, which is 144 here. If you exponentiate with a base of 6, then you have x is equal to 6 to the negative 1 power, which is 1/6. Over here, if you use a base of 4, you have x is equal to 4 squared, which is 16 here. This one's a little trickier. You're going to have to use a base of x. So we have 3 is equal to x to the 1/3. We use a power of 3 on both sides, and those powers cancel each other out, so x is equal to 27. Okay, condense. First of all, when you're condensing, you want to look for numbers in front of logarithms. Now this one's kind of hard to spot, but dividing the entire logarithm by 3 is exactly the same thing as multiplying the expression by 1/3. So that's also a number in front. So these numbers have to go back up top as exponents. So this is the log base 4 of y plus log base 4 of z to the 5th plus log base 4 of x to the 1/3. Now since all 3 logarithms are adding together, we can condense this using multiplication. So all of those terms have to multiply. Y times z to the 5th times x to the 1/3. Question 24, start the same. All of these numbers in front of the logarithm have to go back up as exponents. So this is going to be the log base 4 u to the 5th minus log base 4 of w to the 5th minus log base 4 of v to the 10th. Now you got to take two logarithms at a time. These first two logarithms, there's a minus sign separating them, so when you condense just those two, that's going to be the log base 4 of the quotient u to the 5th over w to the 5th, then we subtract log base 4 of v to the 10th. Now we have to condense these two logarithms. There's a minus sign between them. That means these two expressions have to divide each other. So it's going to be the log base 4 of u to the 5th over w to the 5th. And now we need to divide v to the 10th. Well, dividing is the same as multiplying by the reciprocal. So v to the 10th is actually going to be on the bottom. Okay, 25 is a rather tricky one. Logarithms and radical signs don't play nicely together. That's just something that you'll be best to try to remember. Radicals and logarithms don't play well. Change radicals into rational exponents. So this expression could be thought of as that. A square root is just a power of 1/2. Now, if you distribute this exponent to the numerator and to the denominator, this becomes the log base 5 of x to the 1/2 over y to the 1/4. And you have a power that's being raised to another power you multiply. Now, since we're taking the logarithm of a quotient, we can expand that using subtraction. This is the log base 5 of x to the 1/2 minus log base 5 of y to the 1/4. When you move the exponents down to the front, and you get 1/2 log base 5 of x minus 1/4 log base 5 of y. Now in 26, we have a couple things going on. We have a quotient, but also we have a product down there at the bottom of the quotient. So we need to expand the quotient first using subtractions. This becomes the log base 4 of 8 to the 6 minus log base 4 of cb to the 3rd. Now we have to expand this product here, and keep in mind we're subtracting the entire expansion. So this is log base 4 of 8 to the 6 minus. Now put the expansion in parentheses. Log base 4 of c plus log base 4 of b to the 3rd. Two things we have to now do: move the exponents down to the front and distribute this minus sign right here. So this is 6 times log base 4 of a minus log base 4 of c minus 3 times the log base 4 of b. Now we're getting into the solving equations. For the logarithmic equation, you have to isolate the logarithmic term and then exponentiate both sides. So this is the logarithmic term of this equation. So we have to divide by -3. And we get the equation log base 2 of b minus 7 is equal to +3. Now you exponentiate using a base of 2, because our logarithm has a base of 2. So you have b minus 7 is equal to 2 to the 3rd, which is 8. Add 7 to both sides and you get b equals 15. Over here, the natural log is already isolated. There's nothing in front of it. There's nothing outside of the function. So you can go ahead and just exponentiate using a base of e. E and the natural log are inverses. So you have x minus 1 equals e to the 3rd. Add 1 on both sides and you get x equals e to the 3rd plus 1. And 30 are different types of problems because they have multiple logarithms. So this, for example, needs to be condensed into one logarithm. Same with this. This expression needs to be condensed into one logarithm. So the two logarithms have the same base. That's important. There's a plus sign between them. That means when we condense, these two expressions multiply. So this is log base 5 of x times x plus 6 and that equals a log base 5 of 55. Now that you've condensed the exponentiate using a base of 5, so that just cancels each of those logarithms. So you have x squared plus 6x equals 55. If you subtract 55 to the other side, it's going to equal 0. If you factor x plus 11 and x minus 5, which means that x equals negative 11 or x equals positive 5. Now you always got to check, remember you can only take a logarithm of positive expressions. That doesn't mean that x can't be negative, but what that means is when you plug it into the expression, it has to become positive. If you plug in a negative 11 right here, or if you plug in a negative 11 right here, you would end up taking the logarithm of a negative number. That's an extraneous solution. The only one that works is x equals 5. Here on 30, they have the same base, and there's a plus sign between the two logarithms. So when you condense this, these have to multiply. It's 5 times x plus 10. That equals 2. Exponentiate both sides, and you get 5x plus 50 equals 81. Subtract 50 and you get 5x equals 31. Divide by 5 and you get x equals 31 fifths.
So the problem is here that x that we're solving for is a variable. We can't solve for x as long as it is a variable. So to cancel the base, we have to use a log base 8 on both sides. Log base 8 cancels a base 8. So x is equal to log base 8 of 35. Now with the calculator, you'd have to plug this in to get the decimal of this. So what you would plug into your calculator is using the change of base formula, log 35 divided by log 8. So we get 1.71 approximately. And one thing you could do is check your answer on your calculator. If x is approximately 1.71, you could use a base 8 and raise it to this power right here, because this is what we're claiming the answer is. And the answer is 35. Now question 32, a lot like question 31, it's exponential because the variable is here as the exponent. The exponential term though is just 2 to the x. That's what we need to get by itself before canceling the base 2. So we need to move this 3 out of the way. The 3 is just a coefficient, it's multiplying. So with a coefficient you can divide by it. And we have 2 to the power of x equals 9. So now we are at the same spot we were in question 31. We need to cancel the base 2 using, in this case, log base 2. Log base 2 cancels the exponential base 2. We have x equals log base 2 of 9. And again, using the change of base formula, this is the log of 9 divided by the log of 2. And that's 3.17. And as always, you want to check your answer using the original equation. 3 times 2 raised. Now most calculators have a feature where rather than punching in these decimals all by hand, it's kind of like a copy and paste feature. In this calculator here, this copies this phrase ANS stands for answer, it copies the previous answer, so I'm raising it to the previous answer, and it should equal 27. Okay, question 33. N minus 10 is the exponent, E is the base, so this makes the exponential term right here. Before we can cancel the base E, we've got to make sure that exponential term is by itself, so add 8 to both sides. We're trying to isolate the exponential term. Now that the exponential term is isolated, we can
cancel the base. What we're trying to do is make sure this variable is no longer in an exponent. So we cancel the base e using a natural log. And the final step to getting n by itself is to add 10. And hopefully you recall you cannot add 10 to the number 30 inside the logarithm. You have to add 10 outside the function. So n is equal to the natural log of 30 plus 10. Now the nice thing about natural log is that's a feature on most calculators. Natural log of 10, or sorry, natural log of 30 plus 10 is approximately 13.4. And to check the answer, using a base e and the exponent, or n, it was 13.4 approximately. So I've got e to our answer, 13.4 minus 10. I'm just following exactly what it says here in the problem, and then subtract 8, and that should equal 22. Okay, question 34. We have a similar situation to question 32. We have a coefficient here, 8. 8 is a coefficient of this exponential term, so we need to divide by 8. We have 8 to the x plus 3 is equal to 3. Now we have to cancel the base so we can make sure that this exponent is no longer an exponent. So cancel the base using a logarithm. Log base 8 cancels exponential base 8, and we have x plus 3 equals log base 8 of 3. And subtract 3. So x is equal log base 8 of 3 minus 3. Now we're going to have to plug this into a calculator. Log base 8 of 3 is the same as the log base 10 of 3 divided by the log base 10 of 8, and then we can subtract 3 from that. So log 3 divided by log 8, subtract 3, is negative 2.47. Approximately. And just to check, we should have 8 times 8 raised to a power of negative 2.47 plus 3, and that should equal 24. Okay, question 35. How long would it take 5,000 investment to double if it's compounded continuously? And there's the key word right there. This is continuously compounding interest. So right off the bat, you ought to be thinking about this formula. Where A is the future amount, P is the principal investment, that's what you start with, R is the interest rate, T is time. Now, we know the 5,000 is the initial investment. The interest rate right here is 6%. Remember, you got to change that into a decimal. Now, the actual question of this question is how long would it take? How long would it take is a measurement of time. So we leave t as a variable since we don't know. Now, we can't have an equation with two unknowns. If we have t as an unknown, that means we have to know the future amount, a. Now, it doesn't specifically say it in the problem, but if he says how long would it take for a $5,000 investment to double, then if $5,000 doubles, it's going to become $10,000. So now we're solving for t, and this is an equation much like 33 or question 34. This is an exponential equation because the variable is the exponent. And so what we're going to do is cancel the base e. E is the base. 5,000 is a coefficient, so we've got to divide by 5,000. Now we can cancel a base e using a natural log. So we've got the natural log of 2 is equal to 0.06 t. And 0.06 is a coefficient of t, so we can isolate t by dividing by 0.06. So we get a value of t is equal to the natural log of 2 divided by 0.06. Which is 11.55. And since this is a contextual situation or a word problem, we have to associate this number with what it actually is. This is years. So if you invest $5,000 at 6% interest compounded continuously in about 11.5 years, you would expect your investment to double. And as always, would never be a bad idea to check your answers. So I started with a value of $5,000 at a rate of 6% for 11.55 years. I should expect an answer of $10,000 here. Okay, question 36. We have a culture bacteria of 10,000 and it doubles every 40 minutes. We need to find a function that'll tell us the number of bacteria at time t. So if we have bacteria doubling, or really anything that's doubling at a certain interval of time, then a function that can model that growth is this function right here, where n sub 0 is the initial count or the initial amount. The base 2 represents that this quantity is doubling. That's what makes this an exponential function. T is the time in minutes. A is the doubling time. A is the amount of time required to double, and in this case that's 40 minutes. So actually a very simple problem here, as long as you can remember this formula. 5,000 is our, or not 5,000, 10,000 is our starting count. And there's the function. A natural follow-up question in 36 would be to use the function to estimate the number of bacteria after 10 hours or 40 days or something like that, where you actually have to use the model to make a prediction. Okay? Which would just be nothing more than plugging in a value of time for t. Question 37 is very similar to 36, except rather than a substance doubling every so often, this substance gets cut in half at regular time intervals. And this is an example of radioactive decay. So we've got californium-238 with a certain half-life of 333 days. We have 200 milligrams. We need to find a function. There's two things here. We need to find a function, and then we need to use the model to estimate the amount remaining after 12 weeks. So really two parts to this problem. But the first one is to find a function. And it's going to be modeled using almost the same function as in question 36. But because this substance is decreasing by a factor of 1/2, we use a base of 1/2. And the exponent is still t for time over a, which is the amount of time required to complete a half-life cycle. And in this case, it's 333 days. So our model is going to be 200 for the initial count, or amount. Base of 1/2, the exponent is time over 333 days. So there's our function, or our model. So the second part of this question is use the model to estimate the amount remaining after 12 weeks. Now you've got to be careful. We've set this model up in terms of days, 333 days. So we've got to figure out how many days are in 12 weeks. Well, 12 weeks times 7 days is 84 days. So that's the number that we plug in for t right here. The amount after 84 days is equal to 200. There's a base of 1/2 to an exponent of 84 over 333. So, once you have the model, it's just plugging in values into the model and letting the calculator do all the work. And this is where you really need to practice with your own calculator, because yours is certainly going to be different than mine. You've got to figure out which buttons to push, how to type in an exponent, especially if the exponent is a fraction. Usually on most scientific calculators, when you type in an exponent that's a fraction, it needs to be in parentheses, so just be aware of that. But if you start with 200 milligrams, after 84 days, because of radioactive decay, it would have decreased to 167.92 milligrams. Okay, number 38. A question like this would have come from section 4.5. It's just an application of exponential equations. So we've got this model that models the population of a fish in the lake, the number of fish. So part A is really not too difficult of a problem. Find the fish population after 3 years. So the model's already created for us. All we've got to do is use the model. And since 3 years is a measurement of time, that's going to obviously go in place of t for time. So part A is nothing more than using a formula that's already there. 10 divided by 1 plus 4e negative 0.8 times 3. So this says 7.34, and here's where you really need to read the question through carefully. P obviously stands for population, but you can't confuse this to mean 7.34 fish. P is the number of fish in thousands. So this is 7.34 thousand fish. Okay, for part B, after how many years will the fish population reach 5,000? After how many years is the question. They're asking you to find a measurement of time. So you've got to solve this equation for the variable t, which means we have to know a value for P, population. And the value is, well, we need to have 5,000 fish. But remember, and this is not a trick question, but you know, it's one you really have to be careful on. P represents the number of fish in thousands. So if it's 5,000 fish, then P is equal to 5. So we plug that value of 5 in for P. And we've got to solve this equation for T. Now, right now we've got a fraction on one side, and especially the variable that we need is on the denominator of this fraction, plus the variable that we need is the exponent of an exponential. So first thing we got to do though is try to clear this fraction. So if you multiply a fraction by its denominator, as long as you do it on both sides, that'll cancel the denominator. So I'm going to go ahead and just leave the 5 out of the parenthesis rather than distributing it. So we've got 1 plus 4e to negative 0.8t times 5 is equal to 10. You could distribute the 5, it wouldn't be a wrong thing to do. I'm just not going to do it. I'm going to divide by the 5 right here. So now we have no need for the parentheses. And our goal is to still get this exponential term. E is our base, negative 0.8t is the exponent. So we need to isolate this exponential term by subtracting 1. we got 4e to negative 0.8t is equal to 1. Now divide by 4. And now that the exponential term is isolated, we can get rid of the base, in this case by using a natural log. And finally, to isolate t, you can divide by negative 0.8. So we've got a natural log of 1/4 divided by negative 0.8 and 1.73. And again, this is in terms of an actual context. So we've got to put this in place of its context. It's 1.73 years. Okay, I apologize, there are some typos in this one. Suppose you're driving a car, engine overheats, you park the car to let the engine cool down. This model right here describes the amount of time it takes and the temperature that the engine cools to. So we've got a capital T for temperature and a little t here for time. Part A is asking you to solve the equation for t. Now you have to really understand what this is asking you to do. Since you have an equation here with two variables, big T here and lowercase t here, you're not actually going to, for part A, you're not actually going to give a number like t equals 4 or something like that. You're going to rearrange this equation so that t is the only thing on one side of the equation, everything else is on the other side of the equation. That's what it's asking you to do. And when you have an equation with two variables, that's really all you can do is rearrange it and solve it from one of its variables. So right now the biggest problem is that capital T is inside the natural log. So before we can do anything to try to get at t, we've got to cancel the natural log. The only way to cancel a logarithm, including the natural log, is to use a base. So for the natural log, you use a base of e, and that cancels the natural log. So you've got big T minus 20 over 200 equals base e to negative 0.11t. So we start unraveling some things here on the left side. We need to get rid of that fraction by multiplying by 200. So big T minus 20 is equal to 200 times e to negative 0.11 t. Last step here is to add 20. So the temperature is equal to 200 e to negative 0.11 t plus 20. The whole reason for part A was to answer question part B. Use part A to find the temperature of the engine. So part B could have been done without part A, but part A now makes it much easier because all we have to do is take 20 and plug it in there for t, for little t, because 20 minutes is a measurement of time. So this is just going to tell us how long it's going to take, or what the temperature is going to be if you let the car sit there for 20 minutes on a cold winter day. So the temperature you just plug 20 in there for t. So the work here is just done on the calculator. 200 base e. The exponent is negative 0.11 times 20 plus 20. So it takes, according to this, about 42 minutes. Sorry, 42.16 degrees. I've got the wrong context here. This is a measurement of temperature, not time, so it's 42.16 degrees. So it overheated, just to make sense of the problem here. We were driving the car, it overheated at 220 degrees. So when you stop the car, the temperature of the engine was 220 degrees. What this is saying is after 20 minutes, the temperature of the engine is cooled to 42.16 degrees. So it's pretty cold outside. It cooled that engine down real quick. And that's it.